This video is a continuation from the previous video on variational calculus and the Euler-Lagrange equation. If you haven't watched that video yet, you should watch that prior to watching this one, and a link to that appears above. I also want to mention that since many of you have requested that I make these lecture notes available, there is a link down below in the description for you to download the notes. So in this video, I'm going to introduce something called the delta operator. It's also known as the variational operator, and it's a little bit like the differential operator d that we've seen in differential calculus. So we define an operator delta, and if I would like to take the variation of a function y of x, this by definition is the difference between the varied path y bar of x and the path y of x, which we've previously called the optimal or the extremal path. And this difference is just equal to epsilon times eta as we defined in the previous video. So to be clear, we're defining the variation of y to be the difference between the varied path of y and the original path of y, and that is equal to this amount which we call the variation. It's equal to epsilon times eta of x, where eta of x is a shape function that satisfies the geometric boundary conditions, and epsilon is a small number and is the magnitude in this case. So this implies we could rewrite y bar, the varied path, as y, the original path, plus delta y. And I've just dropped the x dependency for shorthand. Also, we can define the variation of y prime, the derivative of y, as the difference between the derivative of the varied path, y bar prime, and the original path, y prime. And in this case, this would be equal to epsilon times eta prime, since eta is a function of x and epsilon is not. And just to give some context in what we're doing here, I remind you that in the previous video we came up with a condition where the derivative of I bar, the varied integral, or the integral of the varied path, the derivative of I bar with respect to epsilon, evaluated at epsilon equals 0, is equal to 0. We set that derivative equal to 0 to give us an extremal, which in this case is the path that minimizes the integral I. What we're going to show in this video that instead of using this definition here in blue, we're going to use as a definition of the variation this definition up here, where it's just the difference between y bar and y. And I'm going to show in this video that by setting the variation of y equal to 0 is the equivalent of what we did in the previous video. So that's the goal here, is to show that setting the variation of y, del y in this case, equal to 0 is the equivalent of what we did in the previous video, setting this derivative equal to 0, which gave us the extremal. The reason that I'm doing this is because it actually serves us to have both of these approaches. The approach used in the previous video, which is this one here in the blue, it's very useful for deriving things in variational calculus. On the other hand, using this delta operator is a much more practical way for solving problems. When we get out of the first few videos, which tends to be more theoretical and makes use of this result, as we move to solving more practical problems, I'm almost exclusively going to use the delta operator. The textbooks tend to use one or the other depending on which particular textbook, but from my experience, people in structural dynamics do it this way, using the delta operator. This is a lot like we did in differential calculus, when we had the need to define a differential operator d, or d by dx, to replace our definition of the limit as h went to 0 of some function evaluated at a couple different points. But in that same spirit of defining d, the differential operator, we're defining delta, the variational operator. And for the same reason that it's easier in many circumstances to use d rather than this limit definition, we're going to use the delta operator instead of the definition that we used in the previous video, this one up here. Alright, enough said about that. Let's give these some numbers, 1, 2, and 3. And as a result of what's shown in 3, I should mention the commutative property of the delta operator. And in this case, let's say I take the variation del of dy dx. By definition, that is the difference between the derivative dy bar dx, the derivative of the varied path, minus the derivative of y with respect to x. I've just taken this definition in 1, and I've used the function, in this case it's the derivative, and I've made the substitution. But this can be rewritten by taking the differential operator d by dx out and that is d by dx of y bar minus y. But y bar minus y, according to equation 1, is simply the variation of y, del y. So this shows the commutative property. I can take the delta operator inside of the derivative. I can switch the order of the delta and the d operator. Similarly, the delta operator can be shown to be commutative in the case of integration. So the variation of the integral is equal to the integral of the variation. Let's give these a couple of numbers, 4 and 5. So suppose we have the functional f, which is a function of x, y, and y prime. Then using a varied path, the functional f becomes f of x, y plus delta y, and y prime plus delta y prime. And there's an important part to make here. One important difference between the variational operator and the differential operator is when we consider the differential operator, we're actually varying x, dx, the independent variable. In the case of the variational operator, the independent variable is kept fixed, and it's the dependent variable and its derivatives that are varied. That's an important distinction to make. Let's give this a number, number 6. I think I want to expand upon this a little bit. Let me just take the time to do that. When looking at the d operator, we consider two different points on a curve. The first is x and the second is x plus dx. So we're actually varying x. As a result of x, we get some function f of x, and as the result of x plus dx, we get f of x plus dx. The differential operator d or dy can then be written as f of x plus dx minus f of x. By contrast, in the case of the delta operator, we look at a curve, and what we do is we keep x fixed, and we look at a variation of the curve. The variation is something that we call delta y. And notice that in each case we've written it as a function of x, not x plus dx, but just x. And the variation is equal to epsilon times eta, but that's for a fixed location x. In this first case, we're evaluating the function at two different values of x, and in the second case, we're looking at it just for a single value of x. Okay, that's all I wanted to say about that. In order to show that using the delta operator is comparable to what we did in the previous video, where we set this condition that the derivative of I bar with respect to epsilon was equal to 0, I'm going to proceed in the reverse direction from what we did in the previous video. Now, one of the reasons to do this is I think it's useful for you guys to know this stuff forwards and backwards. I mean, literally, you should be that comfortable with it. And after watching this video maybe a couple of times, you'll be that comfortable with it. And the second point is that by actually starting at the end and using the delta operator, it means we can tackle real-life problems further down the chain. We don't need to start at the very beginning. We can start by applying the delta operator in a similar manner to what we're going to do here. Again, this is similar to what we did in differential calculus, where after applying the definition of the derivative using the limits, we could then come up with rules for differentiating things like polynomials or trigonometric functions or exponential functions, and in a similar spirit we'll be able to come up with rules for the delta operator. Alright, so let's get down to business. I'm going to start off by expanding the functional f as a Taylor series. Now we've seen this in previous videos, namely when we dealt with the Runge-Kutta method, and a link to that appears above. But fundamentally, the idea of using a Taylor series is that if we know a function at one particular location, we can use the known value of that function and its derivatives at that location to determine what the value of the function is at another location that is nearby. So the functional f of x, y plus delta y, y prime plus delta y can be written in terms of a Taylor expansion as the functional f evaluated at x, y, and y prime plus 1 over 1 factorial times partial f partial y del y plus partial f partial y prime del y prime plus terms in the order of del squared and higher. So we'll assume that these higher order terms are negligible with regards to this first variation, and so we can ignore it because delta is considered to be something very, very small. It's a variational amount, which means it's infinitesimal. Now what we can do is just simply take this first term over to the left-hand side and flip the sign. So we get f of x, y plus del y, y prime plus del y prime, minus f of x, y, y prime. and that is equal to 1 over 1 factorial is just 1, and partial f partial y del y plus partial f partial y prime del y prime, plus terms of the order del squared and higher, which we'll neglect. Now, if we look at this quantity on the left-hand side, that is just the variation of f, and we can write that as del f, and this little t superscript here on the del operator is to denote that it's the total variation that we're taking. And this just goes back to the definition of what the del operator is. It's the difference between the function of the varied path and the function of the original path. Okay, so this implies, and if we look at the right-hand side, this term over here is actually the first variation of f. So we can write that del superscript 1 to show that it's the first variation of f, and that is just equal to partial f partial y del y plus partial f partial y prime del y prime. Let's give these some numbers, 7, 8, and 9. And let's just pause on equation 9 for a second to notice that the way that we take the variation of a function that is dependent on multiple variables is that we treat each of those dependent variables as a varied quantity, and we take the partial derivative with respect to those in turn. Again, I want to make the point that the independent variable x is not varied. It's held fixed, while it's only the dependent variable and its derivatives y and y prime that are varied. Okay, so finally what we want to do is take equation 8 and integrate both sides of it. So the left-hand side gives us the integral from x1 to x2 of f of x, y plus del y, y prime plus del y prime, dx, minus the integral from x1 to x2 of f of x, y, y prime dx, equal to, on the right-hand side, the integral of x1 to x2 partial f partial y del y plus partial f partial y prime del y prime dx, plus these higher order terms of del squared and higher. This first term on the left-hand side we can denote I bar. It's the integral I along the varied path. And the second term is just the original integral. The left-hand side becomes I bar minus I is equal to, and then the right-hand side remains the same. And let's give these some numbers, number 10 and number 11. Okay, so I'm going to have to continue this on the next page, but let's notice that on the left-hand side, this quantity I bar minus I is just by definition del I. It's the variation of I. So let's do this on the next page. So we can rewrite this as the variation of I. In this case, the superscript t is to denote the total variation of I. It's equal to the integral from x1 to x2 of partial f partial y del y plus partial f partial y prime del y prime dx plus the higher order terms. And in this case, examining this first term here, we can write that as del 1 of I, the first variation of I, is equal to the integral from x1 to x2 of partial f partial y del y plus partial f partial y prime del y prime dx. Let's give these some numbers, 12 and 13. And now, as we saw before in the previous video, this is considered the weak form of the first variation of I because we have a del y but also del y prime. So in order to get rid of the del y prime, we need to integrate this term by parts. So this implies the first variation of I can be rewritten as, and I remind you we want to remove the derivative from this and add it to this term. So the first thing we do is the boundary terms where it's partial f partial y prime del y. We've removed the derivative here, and that's evaluated at x1 and x2. And let me remind you that the variation of y is 0 at both x1 and x2 because we have geometric boundary conditions, in which case the boundary conditions are specified, therefore the variation at those boundaries must be 0. So this first term becomes 0 and can be cancelled. Then we're left with the remainder of the integral, which is this part, the integral from x1 to x2 of partial f partial y minus, and then we've got to take the derivative of this first part. So minus d by dx, partial f partial y prime, and then I've taken the del y out as a common factor, times dx. And this is known as the first variation of I. In fact, this is the strong form of the first variation of I because it involves only del y. This would be known as the weak form. Let's number that 14. Okay, and then we can substitute 14 into 12. So we can substitute for this which gives us that the total variation of I is equal to the integral from x1 to x2 of partial f partial y minus d by dx of partial f partial y prime times del y dx, plus our higher order terms. Now we can make the case that in the vicinity of us finding our extremal, the value of I must retain the same sign. So the idea here is that in order for this to be an extremal, in the vicinity of an extremal, we would expect the integral I to retain its sign. So in order for the sign on I to stay the same, and bearing in mind that the variation del y could be positive or negative since it's arbitrary, we come to the conclusion that everything multiplying del y must then be 0. So let me write that down. So to retain the sign on I, since del y is arbitrary, we need to set this part equal to 0, which, by the way, just happens to be the Euler-Lagrange equation. So therefore, I can draw the conclusion that in order for an extremal, we need to set the first variation of I equal to 0, that this is necessary for finding an extremal. I remind you that it's not a sufficient condition for an extremal. For that, we need to look at the second variation and prove that it's either positive or negative, but it is a necessary condition for an extremal. Now what we'd like to show is it's the equivalent necessary condition as what we showed in the previous video. All right, let's give these some numbers, 15 and 16, and now I'm going to copy equation 15. Okay, so if this is the total variation of I, we again cast our attention to this first term, which we know is the first variation of I, and we go back to our original definition of what we meant by delta y. Delta y is the variation of y, and it was defined earlier as epsilon times eta. So I can rewrite this in terms of epsilon times eta, where all I've done is I've substituted here epsilon eta for delta y. Let's call this number 17, and then I can compare that to what we saw in the previous video, where we looked at the derivative of I bar with respect to epsilon at epsilon equals 0, and we came up with a derivation that showed that this was equal to the integral from x1 to x2 of partial f partial y minus d by dx of partial f partial y prime times eta dx. So therefore, if we compare this equation to equation 17, we find that they're identical with the exception of this epsilon in here. That's the only difference in these two equations. So therefore, we can say that the first variation of I, del super 1 of I, is equal to the derivative of I bar with respect to epsilon at epsilon equals 0 times epsilon. And finally, what it is we're trying to show is that by setting the condition del I, the first variation of I, equal to 0, is the equivalent of setting di bar d epsilon at epsilon equals to 0 equals 0. These are the equivalent operations, and that's what we try to prove in this video. Let's put a red box around it, and we are done. Any of you guys confused? Let's take it from the top. Let's summarize it very quickly what we did here so that we can let it flow. We decided we needed to define a delta operator because it's going to make our life more simple down the line. But I wanted to show both how to use the delta operator and also that in using it, it is the equivalent to the extremal condition, the necessary condition we needed to find an extremal in the previous problem. Namely, the derivative of I bar with respect to epsilon at epsilon equals 0 is equal to 0. That would yield an extremal for the path y of x. So what I did is I came up with this definition. I showed that it was the difference between the varied path and the actual path. We then, and this was the real heart and soul of what we did here, expanded f as a Taylor series. We showed that we could rewrite this as the variation in I, and that when we looked at the first term of the Taylor series over here, that could be defined as the first variation of I. And then we went on to show that if we took the first variation of I, we could compare that to what we had in the previous problem when we did it by taking the derivative of I. And we showed that the difference between the two in taking the derivative of I with respect to epsilon versus taking the first variation of I is the equivalent to just multiplying by epsilon. But when we set these equal to 0, multiplying by epsilon has no effect, and so these are equivalent operations. Well, that brings us to the end of this video. I hope you found something interesting in it. I know it was a little bit mathematical and maybe a little bit abstract, but the framework that we have developed here is going to make life very, very easy down the line. So with that, please go ahead and smash those like buttons. If you have any questions or comments from me, I'd love to hear about it in the comments section below. If you'd like to be notified of new video releases, please hit those subscribe buttons and click on the bell. Thank you for watching, and I will catch up with you in the next video.